My name is Arnie Gunderson. I worked for Pratt & Whitney for 33 years, 20 years of which was on this engine and this wonderful program. I started off as a young junior test engineer, got chosen to go out to the field, and I worked in Flight Test Center for 10 years, right near Edwards Air Force Base. And I got to play with the airplane and the engines for 10 years with a crew of very experienced people. It was a great time. I also, afterwards, took over the overhaul and repair line for the engine back at Pratt & Whitney's plant in West Palm Beach, Florida, and eventually became the program manager before the program was canceled, and I moved on to other things. So I love talking about this program because it was the most rewarding part of my career as an engineer. So the engine, the J58 engine, got started actually before the Blackbird did. The Navy was interested in being able to dash to Mach 3, and so Pratt & Whitney drew out the basic center line of this new engine that could go to Mach 3, but just for a very short period of time. When the Navy found out how much it was going to cost for the overall program to be able to build a Mach 3 airplane, they kind of lost interest. Their business obviously is making ships, and an airplane is just an accessory for them. So about that same time, Francis Gary Powers got shot down on May 1st, 1960, flying over Moscow. And the US government at that point realized we needed something that would go higher and faster to prove invulnerable to what we knew were air defenses at the time. At that same time, a competition then was held between Boeing, Northrop, and Lockheed to see who was going to get to build this new airplane. Separate from that, the CIA approached Pratt & Whitney and said, "We heard about this Mach 3 engine that you built. We would kind of like to pursue that. Can we pick up where the Navy left off?" And that's how the J58 got born. So let's talk a little bit about the basic engine. The basic engine is pretty simple. It's a turbojet, a single spool turbojet. Most modern engines today have got twin spools, one that drives a gigantic fan out in front and another one which is the core of the engine. So if we think about the parallels between these two, this is like the core of a modern jet engine. But it's a turbojet, so it has no normal bypass like those big fans do. We do, in fact, have a bypass, but that came just a little bit later. So let's talk more about what happens at Mach 3 and what drove some of the design features of this engine. At Mach 3.2 and 80,000 feet, which is the design point for the airplane, that's what everything that you see here was designed to do, was to be at its optimal performance at 2,300 miles an hour and 80,000 feet. So all of our design had to do with the heat that happens there too. Air crossing a Mach 3.2 shock wave goes from minus 45 degrees at 80,000 feet up to 800 degrees Fahrenheit. And as it crosses that shock wave, it gets compressed also. It goes from 0.4 psi, almost a vacuum, up to about 15 psi when it's entrained inside the nacelle. And so the engine enjoys seeing nice high pressure air, 15 psi, but it's also pretty hot. That 800 degree air is our cooling air. So what happens when metal gets hot? It expands. This engine literally grows 6 inches in length when it's at cruise, and 2.5 inches in diameter. So how do you design to take care of that? Those were some of the challenges that we had to overcome in making this engine actually work. So we have a little bit of titanium at the front of the engine, the first stage of the compressor. The rest of the engine are various iron-nickel alloys. Waspaloy for the greatest part, some Inconel, one part that's made of an alloy called Astraloy, and that's how it goes. This engine has got a lot of firsts associated with it. It is the very first use of directionally solidified metal. In other words, metal in which the crystals all grow in the same direction. That's right here in the turbine, so that as the turbine blades are spinning, their growth rate is controlled. We know which direction to measure, and the stretch that happens over the life of the turbine can be measured, and we can take maintenance measures to ensure that the blades don't break. But they're very, very strong in that direction, which is what we needed. It's also the first use of self-metering afterburner spray bars and continuous afterburning. We have to, when we light off our afterburner, it can run for an unlimited amount of time. As long as we have fuel, we can run the afterburner. So that's another big first. You may have noticed that there's a little bit of plumbing on the engine. The engine has got 600 pieces of plumbing on it. The plumbing is all made of 321 and 347 stainless, which is very easy to work with and holds up to the heat. Keep in mind, all the plumbing either has fuel or oil inside of it, so it doesn't get quite as hot as the rest of the outside of the engine. The oil is a pure synthetic called polyphenol ether, and it's chemically stable up to about 650 degrees Fahrenheit. We try to keep the oil at about 400 degrees with the use of a fuel oil cooler. When fuel first comes into the engine, after it goes through the main fuel pump, the very next thing we have it do is to go through the fuel oil cooler, because we want to keep our bearings cool and lubricated. So I mentioned computers before. When this engine was built, digital computers were just in their infancy, and they were so big that it was impractical to put them on the engine. And how would you keep them cool? Electronics, as you probably know, don't hold up well to high temperature. So we ended up having to use hydraulic computers, and that's what the control system on this engine is all about. Each of those blocks, one on each side, this is for the afterburner, the one on the other side is for the main engine. Those are actually computers, and they've got cams and levers and valves and stuff inside that are all being driven by what the temperature is out front, what some of the internal temperatures and pressures are, but primarily by what the pilot is doing with the throttle. So all of those inputs are coming into each of these controls. The controls compute what it needs to do to control fuel flow as a result, and all of those tubes are just like the circuitry that's inside any computer type device these days. So those are our wires, in addition to the muscle behind the actuators. So let's talk a little bit about how the engine and the inlet and the exhaust work together. That's the magic of the SR-71 and its ability to cruise at 2,300 miles an hour for about an hour at a time. As the air crosses the primary shock wave off the nose of the airplane, we catch another flow with that spike. The tip of the spike at the front of the nacelle is a very sharp conical device, and then it's also got a little conical shape on the back of it. And at about Mach 1.6, that spike starts to recede inside the nacelle. The inside of the nacelle is conically shaped as well, and so as the largest part of the inlet spike or cone moves aft, the throat of the device, in other words, that narrowest portion, starts to move back and gets smaller as well. That's where the compression and the temperature rise occurs. It's right at the throat. So that's regulating the air coming in. When it gets to the front of the engine, the air is actually split. We've got a series of doors around the outside part of the engine, right in this area right here, and a lot of the air, about half of the air, gets diverted around the outside of the engine, but inside the nacelle. Most modern aircraft that can go supersonic, F-14, F-15, F-16, F-18, all do the same thing. They dump that air overboard. That creates drag. We don't want drag. We want to be able to be efficient at Mach 3.2. And so we keep all of that air inside. We let it flow around the outside of the engine, and then at the back, behind the afterburner, we let that air join back in with the exhaust of the engine, and then we extract all of the energy that we put on that air when we compressed it and heated it up. We run both the exhaust of the engine and that secondary airflow through a convergent divergent nozzle and expand it out again. I'm going to get a little engineering in here, if I haven't blown you away already by that. In order to achieve supersonic flow of an exhaust stream or anything, you have to have a pressure ratio across that convergent divergent nozzle of at least 8:1. In order to get a Mach 3.2 flow off of a nozzle, you have to have that pressure ratio be at least 40:1. So at sea level, that's pretty tough to do because the 1 in that ratio at sea level is about 15 psi. So what's 40 times 15? It's 6,000 psi. So how do you get 6,000 psi inside of a duct? It's very, very difficult. You can do it with a rocket engine, but you can't do it with a jet engine. If we put 6,000 psi back here, it'd blow back out the front of the engine, which is defeating why we've got the jet engine to begin with. But when you're at 80,000 feet, we only got 0.4 psi back here, so we only need to carry about 20 or 21 psi inside that duct. And as we cross the convergent divergent nozzle, lo and behold, we have Mach 3.2 exhaust gas velocity, and we're very, very happy just cruising along. Once you go past Mach 1, the drag on the airplane drops off significantly, and at Mach 3.2, it's not significantly higher. And so it turns out you don't need a lot of thrust at those conditions, and the engine adjusts accordingly. We get about half the thrust we need from the engine, and the other half comes from recovering the energy that was around the outside of the engine when we put those two streams back together again. This is the most amazingly efficient device. We actually recover 88% of the energy that we put into the air at the front of the engine, and then it all comes out the back. There's only a 12% loss, and that's through heat energy. So, what else can I tell you about the engine and the airplane and how our propulsion system works? I'd be happy to answer any questions that you've got. Let's talk a little bit about the fuel. The fuel is another big deal. That was another heat obstacle that we had to overcome. This system uses something called JP7, which is a highly refined kerosene, very similar to JP4, JP5, or Jet A that you might have heard or seen written on a fuel truck when you went to the airport. Same basic substance, kerosene. Ours is refined. It has an extremely low vapor pressure. What that means is that it's very difficult to light. You can hold a match above a container of JP7, it will not burn. What actually burns, now with gasoline, obviously you wouldn't do that because you know that as soon as you did that, you'd have this gigantic flash. With JP7, it doesn't happen. JP7 has to be above 135 degrees before that match will do anything to the fuel. So the part that actually burns is vapor, and that's why we worry about vapor pressure. So JP7 is also used as the hydraulic fluid in our engine. So we put in a lubricity additive and an anti-oxidation additive and an anti-coking additive. Those three additives allow the fuel to be stable inside the engine. The fuel, by the time it gets to the burner or to the afterburner, the fuel is up to around 600 degrees. And then when we spray it in, it burns pretty easy. So starting the engine was a big deal. It wasn't so much starting for Pratt. We had gigantic air starters that we use on our test cells. But on the airplane, there were no portable air starters at the time that were big enough to do the job. Today, it's a different story. We do have now portable air starters. And on the other side of this aircraft is something known as a Buick start cart. And that's what we came up with to start the engine when it was installed in the airplane. It's a fairly low-lying cart And a few of the guys were hot rodders back then. I think there's a few around today still. And it was decided to use a V8 engine through a right angle gearbox to start the engine. Down here is the main gearbox, and there is a starter pad on the bottom of it. It's a open gear cup. And on the start cart is a positive gear that nestles up into that cup and then spins through the force of the V8. It turned out that one V8 wasn't enough. So we ended up putting in two V8 engines side by side, and the engine that we chose was the 1960 through 1962 Buick 400 cubic inch Wildcat engine. It seemed to be the best choice at the time. So that's how we ended up with the Buicks. And since we had JP7 as our fuel, and it may leak occasionally, it turned out to be safe and okay because we had these very short pipes on the Buicks. You may have seen them. And when we were running the Buick cart, we literally had flames shooting out of the exhaust pipes. But the other part that was so cool is the sound coming out of those high revving Buick engines was just amazing. It was like music to a gearhead's ears. So they did have a weak point though. As the Buicks got up to about 6,000 RPM, we finally got up to about 3,000 RPM on the engine. And at that point, when the pilot engaged the throttle to go up to idle, the engine would start and it would take its way up the last 1,000 RPM to our idle speed, which is 4,000. Sometimes the guys running the carts would get a little bit carried away with the noise and they wouldn't drop out at 3,000 RPM engine speed, and they would blow up the Buicks and then puke its guts out all over the ground. Over the first few years, maybe the first 15 years of the program, we broke enough Buicks that we exhausted the entire United States. Every single junkyard in the United States does not have a single 400 cubic inch Buick engine left. We got every one and broke it on this program. So we still had to be able to start the engines. And so a decision was made at that point, what are we going to choose? And we ended up choosing the Chevy 454 engine because there were more of those around than almost anything else. It had the power and the torque that we needed to start, but it never did sound as good as the Buicks. For all of us who were on the program, the Buicks were the best. So, another little story that you might enjoy. When I was in flight test in Palmdale, California, just very close to Edwards Air Force Base, we flew test missions on the airplane before the rest of the Air Force got what it was that we were testing. And so one day we were testing a radar system, and the mission was to fly out of Palmdale, head out to Las Vegas, turn north, head out up over Utah, and north of Logan, Utah, there's a radar range out there. And so we were supposed to shoot down at some radar targets at the ground, come back around, refuel, go back up and do the same thing, and then come back, hang a right turn over Vegas, and land back in Palmdale. So that was the mission. Pretty simple, right? So the pilot and backseater in the airplane finished up the mission a little bit early, and the pilot said, well, I wonder how fast this thing will actually go. And so he's coming down the route from Utah down towards Vegas, and he pushes the throttle all the way up to the firewall, and the airplane starts to accelerate, as you would expect it would. He got going a little bit over Mach 3.4 and swallowed both shocks and flamed out both engines. At about 2,400 miles an hour and 80,000 feet, he's flying pretty much like a hot rock at that point. So he started descending fairly rapidly. The guy in back seat, he has a responsibility of pulling out the emergency checklist and reading off to the pilot what he should do to get things back to normal again. He got one engine restarted at about 65,000 feet, so that we knew we were going to come home safe at that point. And then he got the second engine restarted at about 25,000 feet. Came back into Palmdale, landed, taxied around, stopped and got out. that in itself, we knew something was up at that point, because normally when the guys came back from a mission, where we were in Palmdale, the site next door to us was where the B-1 bomber was being built. And there was this intense rivalry between our guys that flew the SR-71 and the Rockwell guys that were flying the B-1 bombers. And after every mission, after every one of their acceptance flights, they would come over and buzz our building at Max AB. And of course, we needed to return the favor as well. We would buzz their building with our Max AB going on. So this time when he just came in and landed and popped the chute, came in, we said, okay, something is up. We put the ladder up next to the airplane, the crew came down, and he said, there will be no debrief today, boys. And they got in the van and went away. We didn't find out until the next morning when we got our mission recording system tapes back up from Burbank what had actually happened. We didn't know. So I got in to work early that next morning to read my tapes. The Lockheed flight test engineer, my counterpart, did the same thing with his tapes. And I called him up, said, Larry, you see what I do? He said, yes. He says, come on up, we'll go see the colonel. I'm not saying the name so I can protect the guilty. So we came in to his office. He says, come on in, boys. I've been expecting you. Close the door. So the crew and this airplane cannot lie about anything. We record everything. There's voice recorders, there's heart rate monitors. Every single parameter that's on this airplane gets recorded. There's a series of 15 or so different tapes, and each tape has got 15 or so parameters on it, and the data is taken every 3 seconds. So there is no lying about what's going on. So what actually happened was he got going fast enough that he exceeded the capability of the inlet to be able to regulate where the shock wave was. The shock wave ended up getting sucked far enough back that it interfered with the flow at the front of each engine. Each engine then flamed out, literally stopped working as a jet engine. Now we have procedures in place to take care of that. Obviously, he got the engines restarted again, but on a humorous side note, we knew they were very, very surprised because the voice recording of the guy in the back seat, his voice went up an octave as he was reading off the checklist items. So our adventures in the program, some are humorous, some are not quite as humorous, but for the most part, all of us had this incredible esprit de corps and just loved going to work every day. I couldn't believe I was getting paid for this. One other story I would relate on a more personal note, I finally knew what I was working on, because I didn't when I first hired in with Pratt. They said, you're going to go work here. And I said, what's it used for? And they said, you're not cleared, we can't tell you. So they told me even that I couldn't tell my wife what I was doing. I had to tell her that I was working on water heaters, if you can believe such a silly thing. Anyway, I finally am told that I'm going to get to go out to California and work directly with the Air Force, with Lockheed Skunk Works, and I'm going to be at flight tests. So I was pretty excited about that. So I travel out to California, I get up to Palmdale, and the next morning I show up for work, and they walk me into the hangar. And I don't know if you remember the scene from the beginning of the Star Wars movie where Luke Skywalker walks into the gigantic cave or whatever it was, and he sees all of the X-Wing fighters being worked on, and he's just amazed. That is the exact feeling I had walking into the Skunk Works hangar and seeing the Blackbird for the very first time. And I've been in love with it ever since.